Welcome to the course on biostatistics and design of experiments. Today we will continue on the topic of regression analysis. I introduced what is regression analysis in the previous class. Once we have collected sufficient data, you would have changed many input parameters or factors or variables or x's or independent variables as they are called, like temperature or pH or oxygen or agitation, and then you are measuring your output like biomass or product yield. You like to fit a mathematical relation, and that is what is called regression analysis. Okay. You can fit one parameter as the independent fitting the observed data, that is dependent, or you can have two independent variables or 3 and so on actually. Initially if you look at how they seem to be related or correlated as we call it. Okay. If I plot x, that is the independent variable here, and I plot the dependent variable on the y axis, and if the data appears like this, then obviously they are not correlated. Okay. So, when we calculate something called a correlation coefficient, it will become almost 0. As it improves, when you have a good correlation, for example, as you can see, as x increases, y also increases. In such situation, you will have a correlation coefficient tending towards 1. Okay. X increases, y also increases. You can analogous to that, you can have a negative 1 also. That means as x increases, y decreases. So, this type of figures indicate that the correlation between x and y are extremely good, whereas this type of figure indicates that the correlation between x and y are extremely poor. So, between 0 and 1 the correlation coefficient values will lie, and pictorially you can immediately find out if there is a relation. Of course, this is valid only if you have one independent variable at a time you can plot actually. Okay. One independent variable at a time you can plot and get a pictorial visualization. And there are certain mathematical relationship, one is called the covariance, other is called the correlation coefficient, which mathematically tells you how strong is the relation between the x and the y. Okay. The first one is called covariance. It is a measure of the strength of the correlation between two or more set of random variables. So, if you have x and y, I want to see what is the covariance. Okay. Then we do summation of I is equal to 1 to n xi minus x bar y minus y bar divided by n minus 1. Okay. That is called covariance. Xi minus x bar yi minus y bar, where x bar is the averages of all the x's, y bar is average of all the y's, divided by n minus 1, and you sum it up to all the n data points. Okay. Now, a correlation coefficient, correlation coefficient, sometimes it is called Pearson's correlation coefficient and so on, is nothing but covariance xy divided by sigma x sigma y. Sigma x is the standard deviation for the x and sigma y is the standard deviation for the y. That means sigma x square is the variance for the x, sigma y square is the variance for the y. So, they are both related. So, correlation is a scaled version of covariance, okay, because you can have covariance can be a bigger number, whereas when you do this correlation will always lie between 0 to 1. So, it is very convenient, otherwise you can have very large number. As you can see, xi minus x bar, y minus y bar, you can have number practically huge, but once you divide it by this, you are sort of making it lie between 0 and 1 only. So, generally correlation is what is looked at, and as I showed in this picture, you can see the correlation coefficient is varying between 0 to right up to 1 between the x and the y. Okay. Now, so this correlation coefficient, as I said, is also called Pearson's correlation coefficient. So, it is nothing but covariance of x y is this, and that is also represented as Sxy. Sxy means xi minus x bar multiplied by y minus y bar summation. X bar is the averages of x, y bar is averages of y. Now, as I said, this is the standard deviation for x, standard deviation for y. So, this is nothing but square root of Sxx. Sxx means instead of y you put all x, Syy means instead of x you put all y. So, this is nothing but square root of summation of xi minus x bar square, okay, summation of yi minus y bar square, okay, standard deviation, and then there will be okay. This is called the Pearson correlation coefficient. So, Excel also has the function called Pearson RSQ, that is square of the correlation coefficient, or correl, that gives you array 1 and array 2. If you give the array 1 and array 2, it will calculate the correlation coefficient. So, all of them have this type of functions. For example, if you look at Excel, so I put in some numbers, say 1, 2, 3, 4, 5, and I get some y values, just randomly putting it. So, we can say what is the correlation coefficient between these. Correl, it is called, okay, this comma this, oh sorry, equal to this comma this. So, the correlation coefficient is 0.95. That means it is a good correlation, almost tending towards 1, like in this graph, you know, it is very high. So, even when you plot them also, you will be able to see them. I hope you all know how to do plotting in Excel. We can use a scatter plot, okay. So, you can see this, right. So, data as x increases, y increases, it is like a straight line. Okay. So, this number gives you the whole thing, and then RSQ, RSQ square of the Pearson correlation coefficient, okay. That is square of 0.95, square of 0.95, that is 0.95 into 0.95, that gives you 0.91. This is called R square. Generally we use this as when you are fitting data, we use this. This is the top one, correl we use when we are trying to just see the correlation coefficient. So, both are interrelated with each other, okay. Okay. So, so this is called the Pearson correlation coefficient, okay. Okay. Excel also has these things. Type of regression models, like I said, we can have any type of regression models. If you know the physics, you can have, say, some sort of an exponential decay, drug release from a drug carrier may follow exponential decay model. Sine waves, you can have cos and sine, or you can fit this type of binomial relationship, simple regression, b0 plus b1x, b0 plus b1x1 plus bx2, or you can have single parameter cubic x square x cube like this, or you can have two parameters x1 x2 then x1 x2 x1 square, or you can have large number of parameters. So, different types of models are possible, and finally the idea is to get all these constants. These b's are all called constants actually. Okay. So, what you are doing is you are trying to minimize the sum of squares of the error. What is the sum of squares of the error? The data measured and what the model predicts. So, model predicts, suppose I write this as a model, for any given value x it will predict a y. So, that is the model predict, this is the measured value, take a square, and if you summation, that is called the error, and you want to minimize the error. So, this is like an optimization problem where you are trying to minimize the sum of squares of this error. This is called the error, because this is y measured, this is the y model, and the difference square summation is called either error or residual. These are the two names for that actually. So, if you have x and y, you are trying to fit a straight line y equal to ax plus b, and that means you are trying to find a and b, so that yi minus axi plus b whole thing square I is equal to 1 to n is minimized. So, this is basically it is almost like a optimization problem, okay. Okay, that is what you are doing actually. You calculate a and b, so that this is equal to 0. Okay. Now, Excel has two commands, one is called slope, other is called intercept. Okay, this is the slope, this is the intercept. To find out the slope and intercept for the x and y data. Suppose so, let us take the same data. I have x and I have the y. So, if I want to calculate slope, so I just say slope, this is the x data and this is the y data. So, this is the slope of this line, and if I want to get the intercept, so this is the x data, this is the y data, that is the intercept. So, it is having a negative sort of intercept because it goes right down, sorry, intercept C2, slope and intercept. So, we can also fit it using add a trend line command, and we can calculate display equation on different r square and close. Okay. So, it gives you slope and intercept. Oh, okay. So, I have made a mistake here, I think. So, the slope command through the given data set. So, I have to give the y's first. Okay, that is the mistake I made. I have to give the y's first, I have to give the x's later. So, it gives you 2.4. Okay, intercept. Please remember, I have to give the y first and the x later. So, 17.6. So, this is the slope, this is the intercept. So, this is the slope and this is the intercept. So, you can use the Excel command slope and intercept to calculate. Okay, you can use the slope and the intercept to calculate the slope and intercept of a data point. So, do not forget, you need to give the y's first and then the x, whereas for the correlation it does not matter whether you give the x first or y later, but interestingly I do not know why they want the y's first and then the x's later. So, if it is a linear regression, that means if you are trying to fit linear data, it is very simple. We can use the slope command or intercept command, or even I showed you the graphics. We can just draw a graph and then we can say draw trend line, find out equation. So, Excel can very well do. Of course, there are many softwares, hundreds of softwares, commercial softwares on payment basis which can do all these fancy things. Actually, it is not a big deal. Okay. Okay. So, you have to give slope the y first, then the x later, intercept also you give there. So, if it is a least, if it is a second order like ax square plus bx plus c, okay, so then you are minimizing yi minus ax square plus bxi plus c. Okay. I think you can do that also in Excel. Okay, we can once draw this, but you cannot calculate it as slope and intercept, but we can draw it and we can try to fit a second order or higher order type of polynomial in Excel also. So, what are the steps in regression? We have to specify what should be the regression model, linear or quadratic, perform the regression analysis, okay, and then compute the statistics. There are many statistics like r square adjusted, r square predicted, we will come to that, and compare predicted value with the actual value. Okay, for example, like I said, it gives you an idea about the error. What is error? Summation of y calculated my y actual square. Okay, so error should be minimum, so it gives you an idea about that. And if the fit is not good, we can transform it, we can take logarithm of the data. Okay, especially if you look at drug discovery, normally the concentrations you are using is in millimole or micromole, and the response could be some activity. So, normally they take a logarithm of the concentration because millimole or micromole may be very small number. So, when you take logarithm you can bring it down to 1, 2, 3, 4, that sort of thing. So, most of the drug response curves will have logarithm for the drug concentration. Then identify which terms are important. Suppose if you are fitting a multilinear relationship, Okay, suppose you are filtering a multilinear relationship, some terms may be very important, some terms may not be important. So, you can identify which are very important, and you can also plan whether there are any insignificant terms which can be omitted. Okay, there could be some terms which may have very small absolute value, then you can remove that and then again redo the regression model until you get a good regression model. Good means the error should be minimal, the statistics should be quite high. All these generally vary between 0 to 1. So, higher the number, better is supposed to be your fit. Okay. So, in matrix term, this is what it is all about, let us not go too much into that. So, if you are trying to calculate the A and B, that is suppose the slope and the intercept, if you look at it from calculus point of view, we are integrating with respect to say B or integrating with respect to A, and then you are equating it to 0. So, when you do that, we will get an equation for B, and for A it is very simple. Okay. So, because A plus xb is equal to y, so it is very simple. Okay. So, suppose we have 4 factors x1, x2, x3, x4, and we want to fit a quadratic fit. That means it will have a plus bx1 plus cx2 plus cx3 plus cx4 plus d, and then plus that is a plus bx1 plus cx2 plus dx3 plus ex4, and then f x1 x2 g x1 x3 h x1 x4 I x2 x4 j x3 x4 k x3 x4. Okay. And then like that, if you, and then you do that x1 square, x2 square, x3 square, x4 square, what will happen is you will have 1 for constant, 4 for the x1, x2, x3 the main effect, 6 for the 2 level interactions, and then 4 constants for the quadratic. This all adds up to 15, 1 plus 4 5 6 for 15, and you have got only 15 data points. So, there are no error degrees of freedom at all, it will become 0. So, if you try to fit that sort of data, then of course you will get very good fit because there is no degree of freedom at all. So, you better be watching out, you need to have enough degree of freedom for the error, do not forget that. Okay. So, depending upon how many constants you have, and then so subtract that from the total data points you have and check whether the degrees of freedom is reasonably good. Okay. Otherwise your fit, you cannot rely on the fit, you may end up having 100% fit, but in fact the error does not have a degree of freedom. Okay. So, there are many terms such as r square adjusted, r square predicted, which give you an idea about the quality of the fit between the x and y. The first one is called r square, and this is equal to 1 minus sum of squares of the error divided by sum of squares, total sum of squares. This is equal to 1 minus what is the sum of squares of the error? I told you this is the okay, predicted, this is the actual. Okay, this is the predicted actual. So, this is the error squaring up summation, and the denominator has the variance for y, yi minus y bar whole square, y bar is the mean of y. This is called r square. Okay. This is like okay, this is as predicted by the model, this is the total variance, this is the total variance as predicted by the model. So, if it becomes 1, that means the entire variance can be predicted by the model. Okay. So, closer to 1, that means large proportion of it could be predicted by the model, do you understand. So, 1 minus sum of squares of the error, that is given by y predicted and y observed square, and this is the sum of squares of the total variance yi minus y bar square, okay, and 1 minus of that actually. So, generally it will lie between 0 and 1, closer to 1 it means the fit is extremely good, closer to 0 that means it is very poor. So, the degrees of freedom is number of parameters minus 1, as I mentioned some time back also. So, you need to have you cannot have parameters equal to the number of experiments, or number of experiments just matching with the parameters. In that case you will not have any degrees of freedom. So, if I am going to fit a linear relation like y is equal to ax plus b, you have 2 parameters. If you do only 2 experiments, that is not good because your df will be 0. So, you should have done at least minimum 3 experiments, do not forget that. So, but then there is a rule of thumb, number of points should be at least 25% more than the number of degrees of freedom. So, if you take y equal to ax plus b, I have 2 parameters, okay, so the number of points should be at least 25% more than number of the degrees of freedom in the regression model. Okay, so I have 2, so I should even if I do 1, at least 3 or 4, then it is good actually. Next R square is R square adjusted. This is 1 minus sum of squares of the error, okay, multiplied by n minus 1 divided by sum of squares, total sum of squares multiplied by n minus p. N is the number of points, data points, and p is the number of terms in the regression model. So, if you have y equal to ax plus b, p will be 2. If you have y equal to ax square plus bx plus c, then p is equal to 3. So, this can be rearranged also 1 minus n minus 1 divided by n minus p, 1 minus r square. Okay. So, this model tells you something interesting, because you can always add terms and try to improve your r square, but then if you calculate r square adjusted, if you add more terms, p will become large. So, this will become small. So, this whole term become large. So, 1 minus this whole term will become small. Okay. So, r square adjusted will keep going down, although r square will go up. So, p is an indication of whether you are doing an overfitting of your data. So, r square gives you an first level of data fitting, but r square adjusted takes care of the number of parameters you have in your model. So, it adjusts for that here. So, that is a better indication than r square, and if I keep increasing p, you will always keep increasing your fit, but then r square will increase, but r square adjusted will decrease because of p being here. Okay. That is called adjusted r square statistics. There is something called predicted r square. Okay. So, this predicted r square is an indication of the predictive capability of your model. Ultimately, I told you long time back, once I have a model, I can use it for predicting at different conditions. For example, if I have a model yield of the metabolite as a function of pH and temperature, A plus B pH plus C temperature, I do a lot of experiments and then I get the model for ABC. Now, I can use this model to predict what will be my yield of the metabolite at different pH values and different temperature. So, ultimately I am going to use this model for predicting. So, this r square predicted gives you an indication of how good the model is able to predict, whereas the remaining previous are 2 r square and r square adjusted are talking about how good the fit is, whereas r square predicted tells you how good the predictive capability of the model. So, how do you do this? What you do is, suppose you have 10 points, what you do is you remove 1 point and fit your model, fit your relationship, say y equal to x plus b to the 9 points, and then using that you try to predict for the 10th point. So, of course, the prediction will not be exact, so there will be some difference, you square it, that we call it error. Okay. Then you put that point back, you remove another point, and then with the new set of 9 points you fit an equation and then try to predict the value for the data points which was missed out. Again you will get some error, you square it. So, you keep on doing that for each of the 10 points and then you square those errors, add up, that is called the sum of squares of the predicted, understand, that is called the sum of squares of the predicted. So, r square predicted is equal to 1 minus sum of squares of the predicted divided by total sum of squares. What is this? This is summation of yi minus y bar square. Do you understand how it is done? So, if you have 10 data points, what you do is you remove the 10th point and then fit an equation for the 9 points, try to predict the y for the 10th point using the equation you have developed, and of course it will not be exact, there will be some difference, that is error is there, you square it up. Now you put that point back, remove the 9th point and then fit an equation for the remaining 9 points and try to predict the y value for the 9th point. Again you will get some error, square it up, like that you keep on removing one point at a time. Of course you put other points back and then you find out, try to predict the y at that point using the model, and then error, you square it up, you add all these errors, sum of square of the errors, that is called the sum of squares of the error of the predicted, divided by the sum of squares of the total, that is yi minus y bar square, subtract from 1, you will get the r square predicted. This is very stringent r square, it gives you a better understanding of the predictive capability of the model. So, if you fit data and generally r square will be high, r square adjusted will be lower and r square predicted will be still lower. So, ideally if I am fitting a model, I expect all these 3 r squares to be above 0.6, you know, that is a reasonable model, especially with the experimental system. Okay. If you will never get 0.9 on so on for experimental data study. Okay. So, r square will always be high and r square adjusted will be lower and r square predicted will be still lower, and ideally all these 3 r square should be above 0.6. Okay. Then you can be reasonably sure that your model is reasonably good. So, these are the statistics which you need to keep in mind to understand the predictive capability of the model, the fitting of the data and the effect of parameters on the fitting of the data. Okay. Once you do the fitting, you look at the residuals. Okay. That a residual is nothing but the difference between the predicted and the actual. Okay. Generally these residuals should be random, that means if there are 10 residuals, some of them should be plus, some of them should be minus, it should not be all pluses all minus, then you should be, you are very sure that there is a mistake, I mean there is some catch, there is problem in your fitting. So, generally it should be normally distributed, so we can even do a test for normality to see it. It should not be biased in all pluses all minuses, and also a pattern, you should not get residuals like this, you know, it should generally be like this, you know, almost some of them small positive, some of them small and negative. And also you should not have unexplained outlier, suddenly one of the data, one of the residual is very high. Suppose you have 10 data points, you are fitting it, you are calculating residuals. So, 9 residuals are reasonably small, some of them positive, and then one of them is extremely high, then obviously there is some problem. You need to really look at it, look at the data point, that is called unexplained outliers. Okay. Then of course, once you have done the model fitting, you need to validate, you need to see whether it is able to predict for some new x's. Okay. That is very, very important, unless you do that you are not sure your model is good, because you may be, suppose you have 3 points, you fit x and y, you think it is a straight line, but in reality it could be like this. Okay. So, you do not know, although you think by looking at these 3 points they all fall in a nice line. So, you fit a line like y equal to ax plus b, straight line, but in reality it may be going up like this and coming down like this, right. So, you have to be very careful on that actually. So, we need to have a validation, do not forget that we need to have a validation, that is one point. Another point is you cannot extrapolate, because the fit you do is based on the experimental data and you cannot extrapolate from this fit at some other point, which is wrong, because you are not sure how this graph will change. In some region it could be linear, you may think it is a linear relation, but actually the graph may be going up, especially if you look at the biomass, exponential growth phase, all those things happen, right, stationary phase. So, whatever region in which you have collected data and fitted, you have to be sure, you have to use the model only in that range, be sure about it, be careful. Okay. Then there is something called leverage, this is very important, I need to talk mention about it. Suppose you have collected data and suppose this is your plot, you have lot of x data collected around this place and there is one x here. Now you are fitting a line. What is the danger of this? This particular point is leveraging the entire line, slope of the entire line. Suppose if I have made a mistake in this data collection, the slope will change because of this, okay. Whereas even if you make some mistakes here on these points, there will not be much change because you have many points, whereas you have only one point. So, this point leverages your entire slope of this line. So, such an experiment is extremely bad. You should have done at least 2 experiments. So, even if one of them is partially wrong, you are going to take a mean. So, the slope will not change too much. So, the leverage here is only 0.5. You have 2 points, leverage is 0.5. A leverage of 1 implies that any error in collecting data of this point is going to change the slope exactly, whereas if you have 2 points and any error you will get only half. If you have many points 3 or 4, then obviously it will keep going down 1 by 3, 1 by 4, okay. So, that is very important. So, when you collect data it should be well spread out and you should not have points which have a very high leverage like this, watch out. So, how do you change the model to get a better fit? Use a higher order model, you can drop superfluous terms. So, if you have y is equal to a plus bx plus c x2 plus d x square ex 2 square and so on. So, you can look at some of those a, b, c, d, e, and if some of them are very small, you can drop them out. You can use transforms, like I said in drug discovery, concentrations are always in micromole, which is small 0.0001 mole and so on. So, you can take a logarithm of that, okay. Sometimes you can take 1 by that, especially again in drug discovery we use 1 by. So, transformation, we can use even non-dimensional combinations. If you are an engineer, you will know things like Reynolds number. You can even take aspect ratio, length by width, that sort of non-dimensional combination that will improve your model fit. So, some of the common problems that one comes across, reverse causation. This is a very interesting problem, okay. So, in Europe and England they used to see a lot of storks. These are birds, migratory birds observed near the home of newborn babies, okay. So, did these storks bring the newborn babies? June usually brings a peak in the number of both weddings and suicides, okay, especially in the western countries weddings are held during summer time, okay. So, again suicides are also very high. So, which is the cause? Selective observation, selective memory. My spouse never listens to me, forgetting that 98% of the observations where listening did occur, okay. Even if the spouse had been listening to 98% of the time, the 2% of the time when the spouse does not listen is what hits the person, and that gets embedded in the thought process. So, the person may make a statement, my spouse never listens to me, okay, but that could be only 2% of the time, the remaining 98% of the time the spouse may be listening. Omitted factors, okay. There could be some other X's, you know, I may think temperature and pH and carbon is important, there could be a magnesium or some other micronutrient which may be helping the growth of the organism, which is called omitted factors. Multicollinearity, 2 or more X's are confounded. Sometimes the X's may get confounded. Suppose I am looking at weight, height as independent variable and I am measuring the blood glucose level, okay, but then weight and height may be confounded. Taller people may be more heavier than shorter people because height also has some weight involved in it. So, those 2 X's are confounded. So, unless you adjust for that, then that could be multicollinearity. For example, the blood pressure increasing with the say lipid content, but then even age, increase in age also may increase the blood pressure. So there could be a confounding between the age and the lipid content. So you need to remove the effect of age, so that if you want to study only the lipid content, then that is correct, otherwise it is getting confounded. So the multi-collinearity is another problem. So these are common problems you have to keep in mind when you are doing regression fit. Okay, so if you are, suppose you are fitting like this, y equal to b naught plus b1 x. Okay, so you have there is a residual, that is your sum of squares of the error. Suppose I have 5 data points, okay, and I have 2 constants. Okay, so the regression will have 1 degree of freedom, 5 data points, so 4 degrees of freedom. Okay, and residual will have 3 degrees of freedom. So sorry, 4 3 1. Okay, so the total sum of squares, as I said, y I minus y bar. Residual sum of squares is equal to y predicted minus y actual square. Okay, so from these difference we can calculate the regression sum of squares. Okay, residual sum of squares is y data y minus y model square. Total sum of squares y data minus y bar square. Okay, so then we can calculate the mean sum of squares by dividing, as you know, the degrees of freedom. Then we can calculate f value regression divided by residual, and then from the f value and f table we can say whether what is the significance, whether we can calculate p. The h naught, okay, the h naught is there is no relationship, h1 ha is there is a relationship. So if you get p, okay, sorry, if you get the f table, okay, value lesser than the f calculated value, obviously we can say there is a relationship. Okay, this is what you do. So there is an ANOVA which is created when you do a regression analysis. Okay, there is an ANOVA which is created when you do any regression analysis, and there are 3 sum of squares. One is called the regression sum of squares, which is equal to y y minus y model. There is a residual sum of squares which is y data minus y model prediction. Total sum of squares is y data minus y bar square. Y bar is nothing but average y, and then you have degrees of freedom. So total degrees of freedom will be total data points minus 1, and the regression degrees of freedom, if you have y is equal to linear fit, regression will have 1 degree of freedom. Okay, so the remaining will go to the residual, and then you calculate f calculated by dividing the regression by the residual, and then see whether this number is larger than the f table value. If it is larger, then we can say there is the regression relationship is valid, otherwise we will say that regression relationship is not significant. This is how you do the regression analysis and the corresponding ANOVA table. Now suppose this is the regression relationship, y is equal to alpha x plus beta linear. Alpha is the constant term and beta is your slope. So beta is given by sxy divided by sxx. Then alpha is given by y bar minus sxy divided by xxs x bar. Okay. So this is how we calculate both the alpha and beta. Of course I showed you in that Excel, for slope we give SLOPE, and intercept we give INTERCEPT. Okay. So the slope is nothing but sxy divided by sxx, and the intercept is nothing but this actually. This is how the software also calculates. Of course alpha and beta then will have a region of confidence, okay, because it is not single. So confidence limit for the slope, okay, this is your slope, sorry, this is your slope sxy by sxx. So it has got a confidence limit plus or minus t alpha by 2, okay, s divided by square root of sxx with n minus 2 degrees of freedom. Sxx, you know, and s is the standard deviation given like this, s square is equal to 1 by n minus 2 syy minus sxy square divided by sxx. Okay, understand. So you understand this parameter s is given like this, Sxx is a summation of okay, x minus x bar square, okay, that is what it is. This for S square, and this is T alpha 95% if you can put, with the n minus 2 degrees of freedom. Similarly, the intercept also will have a confidence limit, okay, that is given by this type of relationship. The intercept calculated plus or minus 5 by 2 s square root of 1 by n plus x bar square by Sxx with n minus 2 degrees of freedom. So, slope and intercept, because after all the slope and intercept is single value which we have calculated, but then as we have been doing, we should it is like an x bar, you remember we used to always give a confidence region limit. The confidence limit for a point on the regression line, okay. So, if I fit a regression line, so at any point x naught it will give as alpha hat plus beta hat x naught, that means it is predicting the y naught at a given x naught. This is a regression line, okay. This also will have a confidence because it will not be absolute, that is given by plus or minus t alpha by 2 s square root of 1 by n x naught minus x bar square by Sxx n minus 2 degrees of freedom t distribution, okay. So, if I am predicting a y naught at a value of x naught, so it is not just the slope and the intercept alone, there is a plus or minus term coming in here, because there is always a confidence limit. Do you understand? 95% confidence limit is associated with this, and that is given by this. So, you need to consider all these confidence limits for the slope, confidence limit for the intercept, as well as confidence limit for a point on the regression line as well, okay. So, we had completed the regression, which is a very important topic. Once you have a data, you need to fit the data to a linear or a non-linear model with the x's as your factors or independent variables and y is your dependent variable, okay. We will continue further in a new topic in the next class. Thank you very much.